Hey everyone. So we are Nikhil from UNSW and Macquarie University, respectively. So we will talk about photonic quantum computing. All right, let's dive into the world that might feel like science fiction, but it's rapidly becoming our reality. There was a time when our regular computers seemed like magic, but even magic has its limits. Have you ever heard of Moore's law? In simple terms, it's predicted that our computers would keep getting twice as powerful every 2 years. But lately, that's not the case because our computational power has become larger. And photonic quantum computing, instead of traditional computer bits, plays with photons. So, why now? Why photonic quantum computing is important now? One of the reasons is that the traditional silicon-based quantum system, which we like to stack on each other and hoping for the scalability and stability, that is not the case. They have a lot of scalability and stability issues. And one more reason is that photons are naturally resilient against environmental factors, and which makes them increasing coherence times. And uh, the reason is because photons are particles of light and they don't get easily disrupted by their surroundings. So this lets them stay in their quantum state for longer, making them reliable for quantum computations. Also, photonic quantum computing is has a growing demand for powerful computation beyond the conventional classical systems.
Let's not now talk about how it all works to achieve quantum computation through photonics. So this involves three steps. Step number one, we have the single photon generation. We preferably want single photons. Then it's fed through these waveguides, and where we have a control electronics, where we can do our gate operations and create entanglement. And finally, we have step three, where our photons are detected with our single photon detectors. So single photon generation, let's look at the first step. So one of the methods is through parametric down conversion, where a single photon is incident on a nonlinear crystal, and we get two photons. But this process is probabilistic because sometimes instead of getting two photons, we get multiple pairs of photons, which we don't want. So the preferred method is through quantum dot emitters, where we have a quantum dot, a semiconductor quantum dot, and shining a laser excites this electron into the excited state, and through spontaneous emission, as it de-excites or relaxes, we have an emission of a photon, which would usually be emitted in a random direction. But because this quantum dot is kept in this cavity with Bragg mirrors of varying reflectivity, we can direct the uh, photon through a single direction and into our optical fibers. So second step is entanglement and interaction of photons. This is done, as you can see, through a series of beam splitters and phase shifters, which is, in other words, an interferometer. So here we have a ring resonators, which generates squeeze states, which is then encoded passed into our optical waveguide through a dual rail encoding system. And through a series of phase shifters and beam splitters, we can perform our gate operations and create entanglement. Finally, our single photons are read through our detectors. So how's photon detection done? So one of the main methods for photon detection is using superconducting nanowire single photon detectors. And this is where we have our nanowires, and which is cryogenically cooled. And this unlocks its superconducting state. So we have Cooper pairs flowing in these nanowires. And once a single photon is incident on the nanowire, it creates a region of high energy and breaks the Cooper pair. And this transforms this region of the nanowire into a slightly resistive state. And we can then get a voltage signal by measuring, which is measured across the detector. And that's when we know a single photon is incident on our detector. So we have SEM, here's a SEM image of the photon detectors.
Let's look at the potential applications of photonic quantum computing. So one of the applications could be quantum random number generators. Historically, the search for genuine randomness has been tough challenge, and classical methods have their plus and minus, but often they have patterns, no matter how subtle. So in the era where encryption is very important, especially with rising cyber threats, having truly random seed can be a difference between secure communication and massive data breach. So the banks, governments, and tech companies are heavily investing in this technology, seeing its potential. So one more application of photonic quantum computing would be quantum optical neural networks. So the idea of mimicking the human brain has always been a good challenge since the past, and traditional neural networks have made some progress, but they are bound by classical physics, as we all know. So from healthcare industry where rapid diagnosis and treatment plans can be difference between life and death, and the financial markets where real-time data processing can translate to billions in gains or losses, quantum optical neural networking stands to be a game changer. One more important application of photonic quantum computing is quantum cryptography. So let's take a trip down the memory lane. Do you recall the childhood days where we used to use secret languages and codes to share gossips, ensuring that the others were left clueless? So as adults, our secrets grew more bigger, and this isn't just about personal security. So we are talking high level security stuff. So safeguarding national secrets, critical business strategies, and personal information that in wrong hands could be catastrophic. So quantum cryptography becomes useful in these scenarios. So one more application is quantum key distribution. Hmm. Remember the classic handshake method shown in old spy films where agents had a secret way of identifying each other? Now imagine a digital handshake where the secret is so secure that it's almost magical. And whether it's financial institutions handling our life savings or defense agencies ensuring national security, so quantum key distribution is promises to deliver just that.
So let's talk about the latest in photonic quantum computing. One of the companies trying to achieve this is a Canadian company called Xanadu. And what they're using is the a continuous variable type of quantum computation, which means the states are represented by a continuous random degrees of freedom, such as squeeze light, and typically is achieved through the quadratures of the electromagnetic field. So here they use something called resource states, which are highly entangled multiple qubit states, which you can see here, the red and the blue. The blue here is represented by the Gaussian modes, and the red, which is the non-Gaussian, which is the Gottesman, Kitaev, and Preskill qubits. So the Gaussian are what we're used to. This is represented by squeeze light, the displacement operations on light, as well as linear optical transformations, such as that by beam splitters and phase shifters. But the most special element here are the non-Gaussian modes, and this is what leads to helps achieve universal quantum computation. And non-Gaussian character operations of non-Gaussian character are, for example, photon addition and subtraction, photon counting, and generation of cat states. So it's this intermixing of both Gaussian and non-Gaussian modes of qubits, which leads to this very versatile kind of quantum computation. And this helps with robustness. The benefits is robustness against noise and optical losses, and the computation can be achieved at room temperature. So another quantum computing company which is trying to achieve it, their goal through photonics is the Psi Quantum, which is an American company. They're known as a fusion. They're following a fusion-based quantum computing route, where they have once again these resource states, which are entangled, and sets of 4 resource states then have there were 2 photons or pairs of photons being fused together. This is what we see here. And this is an expansive view of the architecture that they use. So what really happens is these 2 photons which previously are non-interacting, are passed through the dual rail encoding system on 2 waveguides, and using a projective entangling measurement known as fusion, or in other words, the fusion gates is also a beam splitter in this case, and eventually after detection, the photonic states are fused with each other. and different fusions happening in different regions can be combined to create even larger sets of entangled states. And finally, each step is probabilistic, so only the successful fusion events are switched out and multiplexed to create even larger entangled states, multi-qubit entangled states, which is what's seen here. So as soon as some of the benefits of this type of fusion quantum computing is as soon as the photons are created, there's no time wasted and they're immediately fused with their neighbors, either immediately or after a delay of one or more clock cycles. And one of the main benefits of this kind of quantum computation is the fusion measurements are used for both error correction and computation simultaneously, which is very advantageous. Also, no transducers are required, such as that in solid state or matter qubits, where you would need to convert electronic information to photons and vice versa. And another benefit is there's no requirement for millikelvin temperatures. The only low temperatures needed is for the superconducting nanowire single photon detectors, but that's about it. And PsiQuantum is planning to reach a goal of 1 million qubits by 2026.
Now let's look at the limitations and challenges of photonic quantum computing. So first is scalability. So as we increase the size of photonic quantum circuits, adding more quantum bits and operations, the complexity grows exponentially. So this complexity introduces higher chances of errors. Maintaining accuracy while scaling up one of the is the significant challenges faced in photonic quantum computing. So another limitation is efficiency. So current photon detectors and sources are not 100% efficient. And in photonic quantum computing, the precision of operation depends on our ability to reliably produce and detect photons. So currently, our photon generations and detection tools are not perfect. One more challenge is the interconnectivity. So photonic quantum systems consist of various components like photon sources, waveguides, gates, detectors, and each of these components has specific roles and ways of functioning. Ensuring that they all integrate and operate harmoniously, especially when they are developed with different technologies or standards, is a challenge. Another limitation is error correction. So, like in any other computational system, errors can creep in, but they are especially tricky in quantum system. So, what I mean by that is just as in classical computing, where we have methods to spot and correct mistakes, in photonic quantum computing, we need advanced techniques to detect and fix the errors. So, these are crucial for the quantum computing. And one more issue is the technological maturity. So what I mean by that is that developing a new technological field is like building a new city. So we are still laying down the roads, setting up utilities, and constructing buildings for photonic quantum computing. This means that many of the tools and devices needed to make it fully functional and efficient are still in research or early development phase. One more issue is research roadblocks. So every computation at its core consists of operations like adding or comparing numbers. And photonic quantum computing, we are still figuring out the best ways to do some of these operations using light.
To conclude this talk, let's summarize some of the points. So quantum computation by photonics provides a good route for low decoherence and with great connectivity and transfer of information. It requires less heavy cryogenics as photons really don't feel heat. So this can be done at room temperature. And there's access to a large amount of degrees of freedom by using, for example, a continuous variable type of quantum computation. And we discussed there's some very useful and promising applications, which is in quantum key distribution, quantum random number generators, quantum cryptography, and quantum optical neural networks. And some of the latest research in photonic quantum computation done by Xanadu and PsiQuantum is proven to be promising for the future as they leverage this kind of measurement-based quantum computation, which uses highly entangled multi-qubit states, such as the resource states, and once again, a continuous variable quantum computing method, which gives access to continuous degrees of freedom to perform the quantum computation. And this is very beneficial for optimizing and leveraging error correction and quantum algorithm protocols, and very advantageous for scaling up the quantum processes. And some of the limitations and challenges which need to be addressed are with scaling up these quantum photonic processes. Look for smooth or seamless integration of different components of the photonic architecture, and find ways to optimize these error correction techniques and computational efficiency. Thank you for listening.